Good afternoon, everyone. Thank you for joining us today. I hope this finds everybody doing well under our current situation and quarantines. Today for this webinar, I want to talk about what we can do with segmented detectors in the TEM. And we have a really broad audience, and so this is somewhat of a unique forum to talk in. But what I want to do is hopefully make it applicable to all of our guests, and hopefully you can find something that will stimulate your mind and hopefully motivate you. But I want to cover a couple of the new techniques that we have now available in CEMAS. And for the non-technical people, it'd be really nice just for you to see what's possible in CEMAS and understand how we go about performing some of the science and what we can see. If you're a grad student currently or a potential grad student thinking of coming here, hopefully you'll see the state-of-the-art facilities we have and the research that's possible, both applied and fundamental. So whether you're here now or thinking about coming, this is a place I think you'd like to be, and we would enjoy having you if you'd like to come. And to the PIs and to the industry liaisons, we're one of the few state institutions that have access to this type of equipment. We have a very rare facility here. And what we want to do is collaborate with people. We want to find problems and we want to identify them and help solve them with electron microscopes. And so if you have any ideas or any problems that you'd like to solve using electron microscopy or think might be helped with electron microscopy, please reach out. We'd be happy to talk with you. This is a broad talk, so hopefully there'll be a lot of questions. You can submit your questions in the question and answer tab. There's also a chat function. If you're having any problems or anything's going wrong, please post it in the chat. And if you put your questions in the question and answer, we'll aggregate them and come together at the end and try to answer them. And I'm happy to talk with anyone offline to expand this further if you'd like. Okay, so at CEMAS, I'm going to talk about the resources and the facilities we have here. Right now, we're under a similar, I think, quarantine as to most people. We are not allowed in our facility, and right now the only external interaction we're really having at this point is this beyond the scope discussion, and we're offering them once a week. So we highly encourage you to join us and ask questions, and we even take suggestions. You can help us guide what talks you might want to hear. As well, we still are doing consultations. So we very much would like to hear from you if you have problems in any of the areas of microscopy, or if you'd just like to talk through what it is you're thinking. Feel free to reach out to cemas.osu.edu or to myself at williams.2156. So a little bit about me to start this off. I started at Virginia Tech as an undergrad. I was in the Corps of Cadets there and got a BS in material science. I then came to Ohio State after a short internship at Wright-Patterson Air Force Base and did my master's and PhD here at OSU with Hamish Frazier. Did a little bit of postdoctoral work and then was a research assistant professor at University of North Texas for a short time before coming back here and starting into the senior research officer position at CEMAS. And now, as Dan said, I'm the assistant director for research and development at CEMAS. Research interests are broad, but they tend to focus on metallurgy, mainly titanium, with respect to aerospace and bio, and now additive manufacturing. A large part of my research has been using microscopes to develop quantitative inputs for models and predictive capabilities. And so what I mean by that is when we break something or when something fails or when something is strong or weak, we want to understand why. And one of the ways we can do that is by characterizing the material and the microstructure in the microscope. And so that's really one of the main thrusts of my research. Now in my current position, I interface significantly with industry. And what we try to do is identify problems in industry that have solutions and can have workflows created using the electron microscopes. And so we really try, myself and as a facility, to answer those questions. And in doing that, we look at samples that are very small. And how do you look at something this width of your hair and try to relate those properties to an aircraft engine or a biomedical device or a car part? And so correlative electron microscopy is something we all are striving to improve here. They ask us to add something fun. And so for me, something fun is back bowls with waste heat powder. Here we have a picture of, let's see. Here's waste heat powder in Park City. And here's about 13,000 feet, 3,000 meters. You know, you want to get up here. It's a struggle to get to the top, but then it's a lot of fun to come down. So, well, that's fun to me. I think something that hopefully is a little bit more fun to all of us would be the CEMAS instrumentation. And, you know, the staff and faculty at OSU have worked very hard to produce a facility that is world-class. It could arguably be considered the best facility in the world. And the reason we make that statement is because every microscope in the facility performs better than manufacturer specification. And sometimes it performs a factor of 2 to 3 times better. And again, if you have any ideas or thoughts that our equipment could be used to your benefit, don't hesitate to reach out. We have $40 million worth of electron microscopes, and they're here to solve problems. One thing I would draw your attention to in this image is this image on the left. This is our Titan microscope. And what you can see in this picture is how nice we've organized the facility so that you can have the instrument operators sit outside the microscope. And from a stability standpoint and operating structure, it works great. But what I want to point out is the size of the microscope relative to the people. You know, this microscope is on the order of 10 to 12 feet tall, maybe taller. And what we put in it to analyze is a sample that is 1,000 times smaller than the width of your hair. And I want everyone to understand that what we're talking about here, we have a machine bigger than 10 feet tall, and we're going to use something smaller than 1,000 times smaller than the width of your hair to do all of the analysis that we're going to show coming after this. And so, you know, understanding how to have a good sample is very critical. You can have the best equipment in the world, but if you don't have a good sample, it's impossible to do the things we're talking about. And so I highly encourage you to attend the next Beyond the Scope talk with Dan Huber, who's going to talk about how you make these FIB foils and part of the way that we go about making these good samples to go in these microscopes. In the facility, we have 4 SEMs. We have 2 dual beam focused ion beams. We won't discuss any of that today. We also have a HeliScan X-ray microtomography unit and an XRD. We have 6 TEMs. If you attended a talk a few weeks ago, Yoshi talked on the Krios and the Glacios TEM and what you can do with cryo-imaging. If you've seen any of the cool images of the coronavirus or of SARS or AIDS or anything, most likely these came out of cryo-electron microscopes. We have 2 microscopes that are very good sort of as a workhorse to train on and to teach and to do classical microscopy. And then we have 2 aberration-corrected microscopes. We have an image-corrected, and then we have the probe-corrected Themis-Z. The probe-corrected Themis-Z arrived just a few weeks before the quarantine set in. So we have some preliminary data, but what I want to talk to you about is what the potential will be when we open back up and what's at our fingertips to really start to explore. So I spoke about this small sample, again, 1,000 times smaller than the width of your hair, that we're going to put in the microscope and start to look at. And the microscope we're going to put this in is our Themis-Z. And I don't want to talk about most of this today because this can be for another talk. So I do encourage you to pay attention to the schedule and see when we're going to really release a talk on all of our possibilities and capabilities. But just some of the ones to speak about. Our system is monochromated, which means we can reduce the energy resolution in the system to around 100 MeV. So for spectral imaging, this is a game changer. We can now start to probe all sorts of near-edge structures and things similar to what we'd probe in the synchrotron. We have the ability to be at high resolution at 60 kV, 200 kV, and 300 kV. And what this affords us is really a significant amount of flexibility in our analytical capabilities. These small samples we put in the microscope quite often are beam sensitive, they damage. And so being able to vary the voltage is important. We can also use the monochromator to vary the dose. And so now you have an analytical microscope where you can tailor the amount of electrons that hit the sample to get the best signal out of it. In doing this, we also have the ability to image features down to around 63 picometers. Now again, with appropriate samples. The system has a Super-X high-speed X-ray collection system. So this allows us, if you've seen any atomic resolution EDS mapping, this allows you to do atomic resolution EDS mapping. It's also equipped with a dual eel spectrometer and DigiScan. So we have the ability of doing the same analysis, but using eels as opposed to X-rays. And eels is electron energy loss spectroscopy. One of the things that makes this system so nice is the improvement in software. And so it has 2 software packages, an OptiMono and an OptiStem package. And What this does is help reduce user error. And that's not in any way saying the user is limited. No matter how good you are, you're basically trying to reduce a function to its minimum when you focus an image. And having software that helps improve that and mathematically quantify that you're at the best focus really helps with reproducibility of data. So for analytical work, this is something you certainly want. And what we'll really talk about today are the two additional detectors that we have with this system, which is a 4-segment annular detector and an EMPAD pixelated detector. One of the real strengths of CEMAS, I would say, is that we've developed remote microscopy for our facility. And it's made possible by the ORNet, which is a fiber optic backbone that runs through the state of Ohio. We have a few different facilities in the state of Ohio that you can actually drive our microscopes from, and it feels as if you're sitting in the facility. But regardless of that, if you want to do research with us or you want to send us a sample, what we encourage and almost ask for is that during that time, you're connected to the microscope with us. And if one of us or the staff is collecting data, the primary researcher is there virtually watching what's being done and guiding that research to make sure that the data is collected in the most efficient fashion. And we really find a huge growth from having this type of synergistic relationship. So keep an eye out and we'll talk more about this. But so I alluded to having this thin specimen, and in a microscope, in the condition we're using it in STEM, what we want to do is take our electron beam and converge it down to a point. And so we have electrons and we try to make them into as small a point as possible. And what the Themis provides is a probe corrector. And that allows us to get this point as small as possible. And if we have a small probe, now we can move that probe across the specimen, right? Left and right, back and forth. And when that happens, the beam is going to interact with the specimen. And the way the beam is scattered, or the result of what happens to that beam when it interacts with the specimen, is very much dependent on the characteristics of the specimen, right? And so that's why we do the work we do. We know that as we put the beam on the specimen, we'll get various signals. And when these signals come out, they'll be scattered to different angles. And that's what this schematic is showing here, right? An angular range that the signal is scattered. And what we have down here are different types of detectors that we would have in almost any microscope. The HADF is going to collect high angle scattered electrons. This is what almost all images you see now that are of atomic resolution, they come from an HADF STEM condition. And I'll talk more about this, but this is a very powerful condition because it's proportional to Z squared. So now we can look at an image where the intensity is based off the atomic number. We have a smaller angular range here in the ADF range. If we have the disk, if we have a beam converge to a point, that means there's some angular convergence here. That means when you come out of the sample, there's an angular deconvergence. Well, that angular deconvergence creates our transmitted disk. And this gives us two types of detection signals. Inside this transmitted disk is what's called a ronchogram or a hologram. So all the information in the microscope is contained in this disk. And if we can accurately collect the disk in this region, we have quite a few options of how we process the data in order to pull out the signals we want. So when you're a microscopist and you have a sample in the microscope, what you try to do is optimize your specimen. You then try to decide what information it is you want to look for. You then optimize these angular ranges and conditions so that you have a detector in the right field of view or the right orientation to collect the signal you want. And that's been a very tedious and time-consuming process for all the time when doing microscopy. We'll talk about how these new detectors can relieve some of that stress. Now, when the beam hits the sample, there's all sorts of interactions. And if you've attended any of our talks or performed any electron microscopy, you've probably seen a similar plot. What we're going to talk about today is everything below the sample. We're not going to talk about the events that are happening above the sample, while they'd be very important. And one that's going to be really important with what we talk about today is going to be these coherent elastic scattered electrons. And what happens here is that you have a very low angle of scatter that stays within the transmitted disk. And the coherent scattering of these electrons allows for momentum shifts. And instead of having a transmitted disk that is uniform in intensity, we will have center of mass variations. And we're going to utilize those center of mass variations in order to provide all sorts of new information that we weren't able to before because it wasn't possible to collect them. We also have these incoherent elastic scattered electrons. This is what forms the HADF image. These are high angle scattered electrons, Rutherford scattered electrons. And so they're important too, and these are going to be the two main signals we use in this process and talk about today. And what I want to start with is getting everybody on the same page so they know what we're looking at when we look at an atomic resolution image. And to do that, I'm going to start in somewhat of a basic fashion and show you an ideal crystal and what an image, an atomic resolution image would look like that comes from that. And so I'm looking at a unit cell for strontium titanate. And if you don't know what that is, that's okay. I mean, we like to use it because it's an ideal material. We know the bonding structure. It's very ordered and it's strongly covalently bonded. So what that gives us is a good sample to put in the microscope that won't damage when we look at it. It's a perovskite material, and we have strontium that sits on the cube positions. We have oxygen, the red atoms, that sit sort of in the diagonal or the body face centers. And then in the body center here, in the center of the cube, we have a titanium atom. And so when we look at this structure with the microscope and we want to see the atomic structure, this is what we would hope we would see. Something of this fashion, a two-dimensional projection of it, right? And so we call it an ABO3 structure, the perovskite structure, because A and B represent the two elements, strontium and titanium, the two heavy elements that are being in this compound. And if we look at an HADF STEM image, I mentioned this, but the contrast in this image, what we're seeing here, each of these dots represent an atomic column. And I said that our sample is going to be 1,000 times smaller than the width of our hair. So that means when we look at this image, we're looking through the sample and we're not seeing one atom here, but we're seeing a thickness of atoms. But with a sample that's only 30 to 50 nanometers thick, the number of atoms that we're seeing on top of one another here is under 100. So we don't have a lot of atoms, but we do have some stack of atoms. And the contrast, if you look, it looks like the face of a die. And these four corner atoms are brighter than this central atom. And that's the Z proportionality of the intensity. So if we show the identification, the green atoms are sitting in the four positions here. The titanium is sitting in the middle. But what we'd like to see, and with all this resolution that we talk about in the microscope, where's the oxygen? That's very important from an engineering standpoint. It's very important for us to understand if there's excess or deficient oxygen, and also where it resides in the sample. So what you're seeing here in this image is as good an image as you can take just about a strontium titanate. It's absolutely beautiful. There's not many distortions in it. It's orthogonal and uniform. We can't ask much more for a HADF STEM. If we take an image of a real sample, this is what engineers are trying to do. If we look in the bottom of this sample, we have a region that looks very similar to what we have over here in the SVO image. And it should be, they're the same. These are from bulk and there should be no distortion. But we have physicists on campus who are doing different types of atomic layer deposition or growth. And what they try to do is, starting on a piece of material like this, they want to grow up atom by atom by atom, a new material on top of this layer. And what you can see here is, as you look at this, there's weird things going on in the top of this image. They may not look bad to you, and they may not be bad, but they're different and not as uniform as what's going on down here. So as a scientist, when you are growing these structures, you want to know what you've done. And there are a lot of indirect methods that you can look at, and that's what they would do in their labs. But when you really want to directly see what's going on, you want to look and see the structure that you've grown. And so what we can see here, if we look along the green line, you can see that a deviation or a distortion occurs, right? And we have these two black regions that form, and maybe an extra plane has been added. And as we look up here, we see a very different looking structure in the top of the image than we do in the bottom of the image. So what's going on there? What are these dark lines, And if you've ever worked in metallurgy or dislocations, these look very interesting in this central region. And if we think that they might be edge dislocations, we can zoom in and actually look in this region, right? And see more closely what's going on. And so now, again, we have a beautiful HADF STEM image. It's showing the positions of the strontium and the titanium positions very well. We can draw in an edge dislocation here. And if you think back to your introduction to dislocation class, one of the things they taught you is that you can draw Berger circuits. And if we draw a Berger circuit around this, we can end up with almost a perfect edge dislocation. Now, if you're thinking about the crystallography and you're looking at the orientation, we're looking down, you might say that it's very interesting to have a dislocation of this character, and that is true, but that's not the conversation for today. More importantly, I'd say there's another dislocation here. And while this is a beautiful image, it doesn't give us all the information we want. There's so much more that a scientist or an engineer would need to really start to answer problems and characterize things. There's a lot here, but it's not all we want. And so what is that extra information we're looking for? Some of the questions would be, what is in the dark region here? Is it a vacuum? And there's some residual contrast there. Is it a different material? Is it a lighter element? What's going on here? One of the obvious questions you ask when you have dislocations is strain. Can we measure the strain around this dislocation? Can we measure the strain close to the core? Can we measure long-range disorder as we move away? Like, what's going on in this region? I mean, how can we quantify it? Do these dark lines, they seem to intersect, are these dark lines creating these defects, or are these defects creating these dark lines? Again, what's going on? And lastly, and probably one of the more pressing questions that we'd really like to know is, where's the oxygen? Where does it sit? Do we have excess oxygen in these dark regions? We can't see it, so it could be there. Do we have deficient oxygen? Is it a void? Is there nothing there? What's going on? And so one way that we now have to probe these questions, and is really going to open new doors for us, is using the new segmented detectors that we have in CEMAS. And those two detectors are a 4-segment annular detector and an EMPAD pixelated detector. And so what I want to do in the talk is go through a few examples of what you can do with these two different detectors and the various material properties you can start to probe and how it opens new research frontiers for us. So what I want to talk about first is the 4-annular detector, or the 4-segment annular detector. And you can see here and here what the orientation of the detector is. It has 4 quadrants with a middle part missing, right? So when I say annulus, if you're not familiar with that term, an annulus is a donut. Think of a donut hole, or a donut with a hole in the middle of it. That's the shape we want, a plate with a hole in the middle of it, right? And so when we talked about the beam interacting with the sample and the concept of coherently elastically scattered electrons, this is where it becomes important. So Gauss's law would tell us when a converged electron probe passes through the sample, it's going to pass through an electric field. Each of the atoms has a potential, an electric field associated with it. And so when the converged electron probe passes through the sample, the electric field generated by the sample's potential will partially or wholly deflect that beam. And that's the momentum transfer I was referring to within the disk. And if we can accurately collect this momentum transfer, which would be the shifting of the intensity in the disk, we have the ability now to measure and track the center of mass changes within this diffracted disk. That is the key now to performing what we call differential phase contrast imaging. And so differential phase contrast imaging is going to be when we subtract opposing quadrants. So if we were to take the A and the C quadrant and subtract one from another, and the B and the D quadrant and subtract one from another, what that allows us to do is accentuate these momentum transfers, or these coherent elastically scattered electrons that have shifted inside the disk. Now, that gives us the ability to characterize both in-plane magnetic distortions and in-plane electric fields, okay? Now, this isn't a new theory or a new technique. The theory came around, I think, in the 70s. In the 70s, and it took time for technology to get to the point that we could actually collect the data and put it to use. Over the years, the past 30 years, there have been individual researchers that have had home-built systems or systems in-house that they have used to do this. And in the 90s, there was some really nice work by Hyder. And then into the early 2000s, Shibata has done some work where he's really detected or created a system where he can detect in-plane electric fields at the atomic resolution. And so what I mean by that is here's your strontium titanate image with an overlay of the atomic positions. Oxygen is again red here. And so we'd see no oxygen positions in this image. However, if we look at the DPC image here, it shows the electrical field potential of both the strontium, the titanium, and the oxygen positions. And we can actually create a vector field map and show how that electrical field is changing around the atomic columns. This is stunning work. There's not many people in the world who can reproduce this type of data at this point. And it really opens doors for how we can now start going and probing the electrical fields around single atoms. I also mentioned here we can look at in-plane magnetic fields. And so that by the same technique that we're looking at this electrical field on the atomic image, if we switch the microscope into Lorentz mode, we can look at magnetic fields. And so what I have here is an example of some Lorentz TEM images showing on the left here what magnetic contrast can look like. You can see these hexagonal phases. But what's important out of this Lorentz TEM image, not STEM or DPC now, is that the edge effects that occur and this interface effect here, right? We're using this color map to give us a scale of the intensity variations or the field variations, right? Well, what's going on at the edge here and at this interface aren't real. Here you can see with no magnetic domains, there's still this weird contrast at the edge that is not real magnetic effect. So while Lorentz TEM has been used for many, many years to help us image magnetic domains, there are artifacts that are present that really get in the way of us seeing what we'd like to see. Well, if we use DPC now, we can look at the orthogonal components of these vectors, or of these fermions, of these magnetic particles. And so what we want to be able to do is remove these edge effects and effects from the grain. And so when we're using DPC, again, we're looking at the momentum transfer. We're looking at the center of mass change that's going to move from the center of your transmitted disk outer to one of the outer edges of your transmitted disk. So when we use an annular bright field, or when we use a segmented dark field detector, that segmented dark field detector is missing the center of its disk. So what that means is we're only collecting the outer edge of your transmitted disk. And most of this grain information, this is a defocused image here, so this is what creates some of the problems. But if you were going to look at your transmitted disk and try to recreate it using a DPC function, most of the grain information and the grain contrast is contained in the center of your transmitted disk. So by using a segmented annular detector, you can get rid of that grain information. And now we can resolve similar helical phases with similar resolution, but we don't have the edge and the interface effects. Now, I don't want to talk too much about this because Nuria will be giving a talk in a few weeks on this specific topic and showing the comparison between this Lorentz DPC and Lorentz DPC STEM. So I highly encourage you to attend that talk if you're interested in magnetic imaging. But this is extremely powerful. The reason we want to image magnetic domains is because this helps control all of our computers, our memory storage devices. You know, if you want a better iPhone that holds more pictures and more music, I guess we don't need music in the cloud, but if you want something that holds more memory and more data, you need to figure out ways to make those data storage devices smaller and more compact, right? And we'd also like to make them lighter as possible. And so what we're looking at now is trying to figure out, can you flip these small domains, make them smaller, but could you write a 0 and a 1 to them? So now could these become the magnetic domains by which we, you know, have memory storage? So this is a very applicable technique and something that people in the memory storage world and in some of the microelectronics worlds really need to help push forward the next generation of devices. So I want to talk briefly, and I don't want someone to freak out because they see this equation over here. We're not going to talk any math, but I want to talk about some of the additional imaging modes that are made possible to you when you use the segmented detector. And so I alluded to that we were using Gauss's law, and that's essentially what I have written here. And what we're doing when we scan the probe over the sample and we collect this DPC pattern or this dark field pattern is we're looking to define a value for E sub r. And so if you believe me that E sub r is proportional to the intensity in the center of mass, which I'm saying it is, then this intensity based on the center of mass is proportional to the DPC signal, right? And so I've just shown you how the DPC signal can be used to image electrical fields on the atomic level. And then if we're in Lorentz mode, it can be used to image magnetic fields, right? And so this is what we're solving and what we're showing, which is a part of this equation for Gauss's law. But Gauss's law, you can take a derivative of Gauss's law, or you can integrate Gauss's law. And so if we take a derivative of Gauss's law, we end up with ddPC. At ddPC, I'm not sure of much of any work to be done in this area yet, but what it gives you is an image that gives you a representation of the charge density. And so now you have an image proportional to the charge density output of your sample when the beam passes through it. And this is an area that I think has room for a lot of improvement and growth, because I'm not aware of many people working in it, and I'm not really sure what we do with it yet. But if we go the other direction and we integrate, we create the integrated differential phase contrast, or the iDPC image. And now this is a really powerful solution to the problem. To come out with the electrostatic potential is what we want, but what makes this so powerful is that the electrostatic potential that we're imaging is a linear response to the electrostatic potentials of the atoms we're looking at. And so I want to talk about this for a minute and explain why that's helpful and what that affords us. So I come back to our strontium titanate image. We've seen this now a few times. Hopefully you're familiar with it. We have strontium in the corner positions, titanium in the middle. And again, oxygen should be sitting here in a diamond around it. But we're not seeing that, right? And what creates the contrast in this image again is the HADF intensity is proportional to the atomic number, Z squared. So our atomic number for strontium is 38. Our atomic number for titanium is 22, and our atomic number for oxygen is 6. So if we square those, we have a contrast value for strontium at 1444 and a contrast value for oxygen at 36. Well, so when you look at that as a contrast ratio, we have a contrast ratio of 40. This is an enormous value. Most detectors, it's hard to have that level of dynamic range. Now, the HADF detector does possess that dynamic range, but we talked about this. The HADF is a highly scattered electron. It's out to a high angle. And so out of this high angle, there's a very low probability of oxygen, which has a low scattering potential and a low ionization cross-section. There's a low potential of the beam interacting with oxygen and getting scattered out to some high angle position. It will happen, but it's just extremely low probability. So we will never collect long enough to see the oxygen. And even if we did, displaying it with a 40:1 contrast ratio makes it almost impossible to display in a fashion that we can see in the image. Well, now if we go to iDPC images that are based on electrostatic potentials as well, but they're proportional to just Z. So now if we look at the contrast ratio, we have a contrast ratio of 38:6. So a factor of, or a ratio of 6.3. Much more reasonable, definitely something we can show in the image and see the variation between. But what really is the win for us here is that we're using the transmitted disk. And so what's most impactful is that as we scan through this sample and we put our beam on the detector, almost all the electrons that go through the sample do not interact with the sample. They just pass through. And so in that fashion, we have a much, much, much larger signal that hits the detector. So what that does is increase our signal to noise on the detector significantly and gives us a much greater ability to see the oxygen atoms as opposed to ones that would have been scattered out to high angles using HADF. And so what that allows us to do now, if we look at an iDPC image of this, is now we have the same structure, blue and green, so strontium and titanium, but in the diamond formation around it, we have our oxygen atoms. Now, what's really nice about the Themis is how flexible it is and how many images you can acquire simultaneously. So if we had to acquire these two images in successive fashion, it would be very hard. You'd have to trust that there were no imperfections between the two scans, and then you would just try to line up the columns with one another. But these images were collected simultaneously because the HADF sits at a much higher angle than the annular dark field detector. And so you can collect both signals simultaneously. Now, something that we don't need to really go into much today, but if you take these 4 segments and you sum the signal, you now have an annular bright field detector. That's the equivalent of what we would have had before we segmented the detector. And so with the conditions that we have set up to collect an iDPC image, we now also have the same conditions set up that we can collect an ABF image. And it's all about how we process the data and having electronics that are robust enough to do these multiple signal processes. And so now ABF is very good and something we've been using for the past 10 years to help give us an indication of where the oxygen positions sit. So now we can actually see where oxygen sits, but it's not directly interpretable. It's not scalable to where there are intensity variations that we could say, this is how much oxygen here, or this is how much titanium is here. It's just a representation of where the local oxygen positions are. So this is really good. Now we have iDPC and ABF and HADF. So taking a set of images like this, we can get almost all we need to characterize the structure. I want to look at a few examples. I'd like to thank Austin and ThermoFisher for providing some of this data. This is work performed by Ian McIlernan at University of Glasgow. And what we have here on the left is the ADF image, and you're looking along a 110 direction, and this is different than what we've been looking at, but what you have are the A atoms, the really heavy atoms sitting in this position, and then sitting in the middle position are the lighter titanium. In this case, it's probably cobalt and magnesium. But what we have here is the integrated DPC image. And I want to draw your attention to these regions. And if we look under the green arrows, what we're imaging and what you can see is that in between these big columns, there's still the B species, but now we have oxygen positions sitting in the middle, sitting here. And if we look in the top portion of the sample and follow this green arrow down, you can see the oxygen zigzag left and right. You know, that can be, that is a direct indication of octahedral tilting. And now we can measure that, we can see the difference. These things will help control electrical and conductivity properties. But in the substrate down here, you can see there's no zigzagging in the oxygen. The oxygen looks to be in a linear fashion, right? And so the ability to be able to visualize this now for the first time is really revolutionary. People have theorized about this. We have abilities to make models and predict what we expect, but now we can actually begin to visually see what's happening to the oxygen structures. Another material system is barium, sodium, niobium, oxygen. This is a material that's been looked at for years and years and years. It has very nice ferroelectric capabilities. It also has a nonlinear optical response. But you can see how complicated the compound is. There's 15 oxygen in a unit cell. And so it was a really nice when we got to the point with HADF STEM, we could start to image the heavy elements. And so now you can start to see how what one might almost call non-uniform or glassy, like the heavy elements look in this case. But what we really want to know is where are the light elements? Where is the oxygen sitting? And so you can identify the barium, the sodium, and the niobium. And you can do that again in iDPC. The beauty of the linear imaging of iDPC is that we can see the heavy and the light elements simultaneously. So now we have the heavy elements, and if we overlay now the light elements, and you can see how the light elements, or the oxygen here, is sitting in these interstitial sites, right? Again, changing what we can do as far as visualizing the structures we have and we make, and then hopefully changing the course of action that we take in our next experimental step. Another thing that I mentioned when I was discussing the Themis is the monochromator and the ability to change dose. We have the ability to essentially turn the current up or down. And zeolite is one of the most beam sensitive materials you can have. Basically, when you put it in the microscope and put it in the beam, it disappears. And so with some of the functionality that afforded to us in the Themis, you can take very fast frames at very low current. In this particular case, it's under 1 picoamp, and now start to sum them together. So if we take a stack of images and sum them together, we call that digitally correlated frame integration. You can actually resolve the oxygen positions and oxygen structure of a zeolite at extremely low doses. This would not be possible if we just tried to take an image of it under normal imaging conditions. The last example I want to show and talk about is explaining how this increases our resolution and how this technique is also possible at the ultimate resolution of the microscope. And so Emmer did some work while he was with FEI and now ThermoFisher. This is published in Scientific Reports. But what we're looking at is gallium nitride. So we have a heavy element in gallium and a very light element in nitrogen. And these are the models of how, well, what the 110 and the 211 would look like. So we have gallium in green and nitrogen in blue. And then down the 110, we have two various spacings. We have 195 picometers and we have 112 picometers. But when we really want to test the resolution, what you'd like to find is something that has a very tight spacing. And so down the 211, we have two gallium atoms and we have two nitrogen atoms forming this quartet here. And when we take an HADF image or a iDPC image, you would hope to see all of these. And what we've shown is that the nitrogen will not resolve when looking at HADF. But if we look at an iDPC image, you can start to see the perfect correlation. If I draw your attention to these four here, and as we go back and forth, you can see the two bright green atoms represent the two bright columns here and the two weaker atoms. Now, one thing you always want to do when doing this work is do image simulations. So you take a perfect crystal structure you have and run it through some type of multi-slice or MuSTEM model, and that produces an image simulation. Nicely, our image simulation almost matches 1-to-1 with our experimental image, right? And so now if we zoom that up, you can see the actual, this is the experimental image. We have two gallium atoms and two nitrogen atoms. And this is where we would define and say our resolution in this microscope is around 60 picometers. We can resolve these structures clearly and definitively. And again, I don't need to be sensationalistic and say how great this is. I hope you realize until recently, we had no way to image atomic resolution until a few years ago very well. And now we've made such technological advances that not only can we image almost distortion-free in atomic resolution, but we also can image light elements all the way from nitrogen and oxygen. One thing I'd say, and I don't have in this presentation, is some really nice work from a gentleman in Europe, I think out of either Antwerp or, I think it was Antwerp. I can look that up if you really want me to. He recently imaged hydrogen in a titanium hydride. So if we're looking at nitrogen relative to hydrogen, nitrogen is really heavy, right? So in titanium hydride, he had a nice strongly bound material that had hydrogen present, and he could produce a very similar image with the oxygen position or the hydrogen positions present. So we actually can even image hydrogen now in certain materials. Now, those are the things we can do with the four-quadrant segmented detector. Now I want to move into and really start to hit on what we can do with the EMPAD. And the EMPAD is a pixelated detector. And when we look at this diagram that I showed initially of the beam interacting with the specimen and the different detectors that we have down here, a question you might ask yourself is, well, can you collect all of these detectors at one time? Is there a way to collect all the signals simultaneously? And the answer is in some microscopes, yes. And depending on the operator, the answer might be yes. But typically it's difficult, and so what different manufacturers and different systems have been trying to do is create optics and geometries where you can get all of these signals at one time without occluding or without blocking one of the other signals. But imagine if we had a direct electron detector. And if you're not familiar with a direct electron detector, I'll talk just briefly about it, but each pixel in this detector, well, I guess I should say, on these detectors first, these are pieces of silicon, and they have very large sizes, right? On a 4-quadrant detector, there's 4 quadrants of silicon. And so anything that hits that piece of silicon is read out as a charge. So the discretization of that annulus is not very big. There's only 4 pixels, if you will. Well, imagine taking that and now creating a pixelated detector where each pixel on a detector is its own readout or own silicon chip, right? So now we have the ability to put this detector across the whole diffraction space. And when we do that, we can read out an entire diffraction pattern for a given probe position. And so that's what I'm showing here, is that if you have a crystal and the beam is hitting it, a diffraction pattern will come out. The pixels in the detector allow you to have this full diffraction pattern at the 1 pixel that the beam is at, right? So we can capture the diffraction patterns as a function of probe position on the specimen. Now, what this gives us is access to quite a few different processing conditions and material parameters we can start to measure. What it also does is it creates a full image from the detector for each pixel position. This creates big data, big data. The data is very robust, it's data rich, and it has a ton of information in it. But for our EMPAD detector, if you collect an image at the maximum resolution, each image is 17 gigabytes. So think about if you don't have 17 gigabytes of RAM on your computer, you can't even open the image. And most of us still don't walk around with 16 gigs of RAM on our laptops. So that one image is difficult to process. Other companies also make these detectors, and some have higher resolutions. Gatan is a company that makes these detectors as well. You can use their direct electron detectors. If you're familiar with Gatan's detectors, they have 4K by 4K pixels. That means 4,000 by 4,000 pixels. So when you collect an image or a data set, the diffraction patterns are enormous. Enormous to the point that instead of one image being 17 gigabytes, one image can be over 500 gigabytes. So that takes special servers, special data transfer, special everything. Even to collect the data, might as well process the data. What we've developed in CEMAS, at least, is a system that we have servers and in-house processing and very fast data transfer that we can collect our data and hopefully process it and analyze it in real-time fashion. When we do that, it really opens the door to quite a bit. If you capture all the information from the diffraction pattern, it's like walking away from the microscope with all your microscopy information, as opposed to what we used to do was take a snapshot of it and then have to explain all the things we did and keep a lab notebook and all this stuff. Now you can perform bright field imaging, dark field imaging, ADF, HADF, DPC, iDPC, etc., all by taking one image with the right diffracting conditions. There's new things that become more possible. Medium range order fluctuation microscopy is a new possibility for characterization. Strain mapping becomes very possible with this, depending on the resolution of your pixelated detector and the displacements you're trying to look at. You now can do orientation mapping. You can do packed bed analyses and much more. This is just a brief list, and I think there's going to be more that comes out. But hopefully by the time we finish talking about this EMPAD and this pixelated detector, everyone can see the potential for it. And hopefully in 10 years, when we talk about it, we're not talking about it as the EMPAD pixelated detector. We're talking about it as the STEM detector. If technology improves and resolution improves and data transfer and data storage and all these things keep improving the way they are, this will really become probably the way that or the method that we use to collect almost all the information in the microscope. Dr. Janu Wong is going to be giving a talk on this on August 19th. So if you're interested in 4D STEM, I would highly recommend you attend his talk. I'm going to give a brief synopsis of what our EMPAD detector is and sort of how it works. Again, We have a beam that intersects the sample, it puts a diffraction pattern down, and each of these pixels now has a very high dynamic range. Each pixel can hold 1 million electrons. So what this means is if we put the transmitted disk versus a diffracted disk, we can collect all the electrons that are hitting the detector. And that means we have all the information that was in the diffraction pattern. What's really impressive is not only can it hold 1 million electrons, it can count 1 electron. So when you have very weak scattering objects, or you have, in this case here, we have graphene, you can still pick up diffracted reflections from such a weak scattering object as graphene on this detector, because there is more than 1 electron count localized onto a pixel. When we look at the acquisition speed of it, I hope you can see the movie playing up here. This is a real acquisition. So the image is scanning up. Here we have a diffraction pattern. In the middle of it, you can actually see the ronchogram and the various phases going on in the middle of this disk. Again, showing the dynamic range, and there are virtual apertures put on here that can be changed over here and show different images with different information. What's also nice about the EMPAD is it works from 30 kV all the way up to 300 kV. I will say that this system works best at the highest voltages, so we tend to like to work at 300 kV with this detector. Our EMPAD is 128 pixels by 128 pixels. All EMPADs, I should say, are 128 by 128 pixels. For where we are technologically right now, that is probably the largest pixel density we can have, right? And this may seem like a low pixel count when most of the images you take are 4K by 4K now. But again, this is the camera pixel count. This is how many pixels are on the camera. We can actually acquire an image of 512 by 512 pixels with each diffraction pattern being 128 pixels squared, if that makes sense. So I think I mentioned this, but just to be clear, this is a detector out of Cornell. David Muller's group helped develop this. It's been purchased by ThermoFisher and is marketed by ThermoFisher, and it's delivered with ThermoFisher products. For completeness here, I will say there's also a Medipix device, and then I also mentioned the Gatan camera. Both of these have higher pixel densities, but are not nearly as streamlined and easily usable for you know, a researcher in a facility. So let's talk about how, or what actually happens when we look at a sample and what the EMPAD can provide us. So I'd call your attention to Colin Office. Colin Office has been working in 4D-SEM now and really pushing this field and being a leader in it for the past few years. Colin is at NSEM in California, and I've taken a few diagrams from his presentation to use as examples and show you. But so what we have here is a crystal, and what this is representing is 3 different crystals with different orientations and grain boundaries. And what happens when we put a converged beam on one of these regions is you either get out Kikuchi lines, which you usually do. If the sample's thin enough, you won't see the Kikuchi lines, but you'll just see the diffracted intensities. And this is what we would call a seabed pattern, a convergent beam electron diffraction pattern. And as a microscopist, this is what you see in the microscope all the time. And we start to relate what these structures are and just naturally see the crystal structure. But if I want to see in this red grain and know what comes from this diffracted intensity, I need to tilt the crystal so that this diffracted intensity comes to the middle of the sample, so it's on the optic axis. I'll then insert an aperture that will block out everything else that you're seeing in this diffracted region. And then I'll just use the intensity coming from this one reflection to produce an image. And that's a very powerful technique. That's what we've used since the 60s to characterize dislocations, to look at what different phases are present in given diffraction spots. And as you change your cross grains, you start to see how this will change, right? And as you're more off zone, you tend to get only 2 because of the reduction in symmetry, right? Well, this is a tedious process. Tilting a sample on zone requires precision from the operator in the microscope. Putting apertures in and out is an imprecise action. Often they don't go in the right spot. And if I wanted to do the same measurement from one grain to the next, I have to tilt the sample independently, sort of reset everything, then as a good operator, bring it back to that initial starting condition so that I have the same condition for both grains. This isn't necessary anymore with the EMPAD. As I mentioned, the EMPAD is allowing for full dynamic collection of full dynamic range of the transmitted intensities and the diffracted intensities, and it can count single electrons. So if it does that, now that we have a camera robust enough to provide a data set this rich, we have the ability to use virtual apertures of any shape and any size we want. And what I mean by that is this is a diffraction pattern off of the EMPAD. You can see the pixelation, so the 128 by 128 pixels. So instead of these being sharp reflections, you can actually see the pixelated intensity. But now I can choose any one of these reflections and put an aperture around it. So this blue circle here is indicative of me putting an objective aperture into the microscope. And now when I reproduce an image based off of that intensity, I will see a similar dark field image to what I would have seen in a classical TEM image. And here's a few examples of what I mean. This is an aluminum silicon alloy that I'm looking at. I've made the sample using FIB. And some of you may be aware, the FIB uses a gallium ion beam. And gallium is extremely damaging to aluminum. If you take a drop of liquid gallium and put it on a piece of aluminum metal, the metal will fall apart because the gallium diffuses in and damages the aluminum so heavily. So making FIB foils and making TM foils from a gallium FIB when your sample is aluminum is not ideal. But one of the things we want to do in this is try to find second phases. And so if you imagine we made this sample and we put it in the microscope and we looked at this image, there's all sorts of what look to be circular precipitates in this image. They vary in size. Some are small, some are large. And so this is the virtual aperture I used to create this image. I took one image with the EMPAD and I put an annular detector around it, right? This is my donut detector. Now this isn't really an HADF condition, it's more of an ADF condition, an annular dark field condition. And what that means is when we do that, we're going to contain more of the diffraction information. So I can't say that the intensity in this image is based on Z contrast. I can't say that these are heavier in elements than the darker region here, but I can tell that there's something there that I'm interested in and I want to know what it is. Now, if I'd taken an HADF STEM image, that would be all I could do. I'd have to still be in the microscope and I'd have to still look at it. I'd probably want to do some EDS. I might want to tilt the sample and look around. Again, you could spend an hour or two verifying this for yourself. But here I took one image and didn't know the answer. If I place a G vector on this, or a virtual aperture at a G vector of the O bar 22, now I can see that I get rid of all sorts of information. And some of these circles actually start to look like zebras. I've got lines going across these zebras, these circles. That's interesting. And if you've ever looked at defect contrast, you might notice that as a beating contrast. Well, what happens when I look at the negative G? So if I look at the O2 bar 2, as you do this, you're going from plus and minus G, and I don't need to go into what that means, but it changes the diffracting vector that we're using. And you can very clearly see now how the image changes. And for metallurgists out there and people that do dislocation analysis and contrast identification, I think you'll immediately see the power in this. We can see the beating structure still. We can see the circular dislocation loops. And without explaining why, just so you know, these aren't second phase precipitates. These are all ion damage dislocation loops or dislocation structures that were formed during the FIB processing. So if you don't know what you're looking at and you go in the microscope and you want to go show your advisor or someone that you have beautiful second phase precipitates, you're going to be wrong when you go show them this HADF image or this ADF image. If you're critical in your analyses here, and with the EMPAD, that means taking one image, you can go through and verify what you have. A similar effect is possible when looking at dislocations. So when we look at metals and we want to understand, the strength of materials, one of the things we often want to know is the dislocations. What type of dislocations are present? What are the strengthening mechanisms? How are they working? And when you do that, you want to be able to see the dislocations. And so when we look at a material on zone, we're in a very high diffracting condition. And so what that usually gives us is an image that contains all of the dislocations. And so dislocations are these lines here, these squiggly things that look like hairs on my sample almost. And this is again an HADF image. So I'm on zone, I'm looking down a cube zone here, and you can see the structure. Now, if I excite a G vector here, if I excite an 002 G vector, one, you can see how the image contrast changes. If we were really critical, and I draw your attention to this region right here, and you look here, here we have what looks to be an X of dislocations crossing, but this portion of this dislocation is missing. We've created an invisibility criterion. So just as you would do in the microscope to go through and do G.B analysis and create different extinction conditions to determine what a dislocation is, the same is possible here. And now what happens if we go out to a weak beam condition? So if I go out to my 004 reflection, I think this is really interesting. Again, what you would expect here is that the dislocations tighten up. So we're looking at higher strained regions now by going out to a higher diffracting vector. And what you can see is that some of these dislocations become much more clear to see. There's not as much residual contrast around them. The extinction conditions, the invisible dislocations, are more invisible. But what might be really interesting is you notice a bunch of speckle, all these little bright spots. Now, if you're being critical of this image and asking what they are, as you should as a good microscopist, what we can see is that, or what we know is from the image I showed before, is that these are ion damage. These are dislocation loops that were created from the gallium beam. And at its lower magnification and at a weak beam condition, I can light up all of the ion defects and show how damaged my sample is and all the fine defects. It's also telling me that that information is not so well contained in the 002 reflection, but it is in the 004 reflection. So again, if you're familiar with, I don't want to go much more in depth into this, but if you're familiar or do metallurgical work or dislocation work, I hope you see the potential. This was one image that I then spent, an hour processing, as opposed to 2 hours in the microscope trying to collect the data. Now moving on to strain mapping. I mentioned when I showed that first dislocation image, how cool it would be if we could measure the strain around a dislocation. And one of the things that you may have seen in the literature if you're following this work would be what I'm about to show here, geometrical phase analysis. And so when we look at this, this would be a perfect crystal with two different materials grown on top, or a KNN grown on top of strontium titanate. Here is a region of the KNN grown on top of the strontium titanate that has an extra lattice plane. Now again, this is a textbook definition of a dislocation, if you will, or an extra lattice plane. And so what would be interesting is if we can measure the residual strain or the strain around this particle, right? And so one way that people do this is by creating an ideal motif, right? And so what I mean by that is we can take a portion of this crystal that we assume to be undeformed and measure out exactly where the atomic positions are. And then if we create a motif like that we lay over the whole image, any displacement from a perfect position would indicate local strain. And so there you can calculate the displacement from the ideal positions and calculate strain. And this has become very popular over the past 10 years with the improvement of probe-corrected microscopes. So people have the ability to collect atomic resolution images, and you'll read in the literature that you can have better than picometer precision in your image. And while that is very true for a perfect image, if you just took this undeformed region, I would argue that it's very difficult to do the same thing in a strained region. But we're doing it anyway because right now it's one of the best ways we have to probe local strain. And so this is what comes out when you do this. If you took this perfect region and used this as a 0, then if this was ideal in my case, what I would say is all of these in-plate strains should be 0. If this whole substrate is unstrained, there shouldn't be these modulations, because red to green here is saying that we've got maybe plus or minus 0.5% variation to maybe plus or minus 1% variation. But when we look here at the dislocation, or the extra half plane, now if we look at the in-plane stresses versus the shear strain, you can start to see how that in-plane does create some distortion. This is a great, I don't want to call it qualitative because we have numbers on it and we're trying to put error bars on it, but it's a rather qualitative assessment. It's not how you want to measure strain. Classically, the way we've measured strain is using convergent beam electron diffraction, CBED, the very same imaging condition that we're using when we're in the STEM microscope. And so what I mean by that is if we scan the beam over a sample and we have a densely packed material and a slightly less packed material, the change in the lattice, or the change in the diffraction pattern changes as the lattice parameter changes. And CBED is extremely sensitive to local strain and local lattice displacements. So having a camera like the EMPAD to be able to measure these diffraction patterns gives us a way that we can very accurately measure strain on the local region. And we don't have to use some scanned image that has distortions in it to do that. We can actually use the diffraction pattern, which is giving us an indication of lattice plane expansion or contraction. Mike Mills, the chair of our department, works in nickel-based superalloys very heavily. He actually works in nickel-based superalloy 718. He and I did some work with one of his graduate students, 5 or 6 years back, or maybe even 7 years, a few years back, let's just say, trying to identify what's in the slide. And so in nickel-based superalloy 718, depending on how you heat it and cool it and work it, provide mechanical treatment, you can nucleate and form second phases. You will nucleate and form second phases. And identifying those phases is difficult because the crystallography of those phases overlay one another. And so what we have here is an integrated diffraction pattern. And you can see the green reflections, and you can see the green reflections here. And so this green reflection on the out is the matrix, and that's here showing what we get when we use that reflection. We have gamma double prime, and there's 2 reflections that help here. We have the 100 reflection and the 001 reflection present. And you can see that by the blue and the red reflection. So these blue and red reflections are giving us these 2 images. And then if we look at the gamma prime reflection here, that's what these green on the corners are. Right? Well, if you look in this image, you can see there's circular features and plate-like features. And we know that the gamma prime reflections also contain the gamma double prime 001 reflections. So what Mike and I and Don McAllister did was use EDS. If you wanted to determine the phase of a material, usually you want to know the crystal structure and you would like to know the composition. And so we used, when the Super-X came out and we had new EDS capabilities, we performed EDS mapping on this in order to show the composition versus the crystallography and show these various phases. But that's a lot of work and a lot more processing and a lot more data collection time. Just how we've used this image here to create these various reflections, we can use this image to put an HADF around it, or an ADF, an annular dark field, which is down here in this corner. When we do that, as I've said before, the annular dark field image, or this HADF image, is proportional to Z squared, the atomic number. So I don't have an absolute value or an EDS signal to tell me what the composition is, but I know that the brighter features in my ADF image are higher in Z. And so by knowing the compositions of gamma double prime relative to gamma, I can show, comparing the ADF images to these various reflection images, what is a given particular phase or particle. This could have taken hours, maybe even multiple microscope sessions to do. This is, again, one image in the microscope using the EMPAD. It's truly stunning how much information is contained and what you can do with it. I have a couple more things I want to talk about here before I finish up. Dr. Wong will go into this much more in depth in his 4D STEM talk, but fluctuation electron microscopy is a technique you may have heard of. So if you have a crystalline material, we get a nice diffraction pattern. If we have an amorphous material, we get a really nice amorphous diffraction pattern. Something in between here, like a glass or a bulk metallic glass, you have short range ordering or medium range ordering that we can start to probe. So what that means, and what we're trying to do with this is we scan our beam over this sample and we probe different positions. You're going to have various sharp reflections form with some angular component and some despacing. What this allows us to do now is start to probe medium range order. So if we want to look at glasses or bulk metallic glasses or highly disordered materials, it's been very hard to have an understanding of the structure. So when you want to do structure property relationships or correlations, we don't have any information to give to the modelers or the researchers. This is one of the first times you can go through now And these bright specks can be related to short range order of given lattice parameters, or sorry, these bright specks can be related to medium range order of these from the diffraction pattern. And now you can create a 2D map showing where things go. You know, if you're non-technical, what this is, one of the things, many things that this could be used for are bendable phones and flexible electronics. So things you see in the movies, things you see that we're moving towards, having an LED screen that when your 3-year-old happens to throw the baseball at it, it doesn't crack, things like that. You know, these are characterization techniques we can use to help probe that type of research. Now I want to finish up with where I started, which is talking about the magnetic imaging with the EMPAD detector. And we started talking about magnetic imaging with the 4-quadrant detector. So if I come back to just refresh your memory of Lorentz TEM, now this is just using the microscope in a normal TEM mode, we have these artifacts that form at the edges and at the interface between the fields. Now what we'd like to be able to do is see both the magnetic contrasts and these interfaces and the regions between them. And I alluded to this earlier, but in order to do that, and when using the segmented detector, the annular detector is cutting out the central portion of your transmitted disk. So what we're measuring are those coherently elastically scattered electrons that are on the edges of the disk. So we're inherently filtering out something that creates noise. And that's good when using the EMPAD or using the 4-segment detector. But what if you actually want to see what's in that noise? What if you want to see the grain orientation contrast that's in that central portion? The EMPAD provides a way to do that, right? So just as we've been showing, we're collecting the entire diffracted disk and then using virtual apertures. The same is possible here. So if we use a segmented virtual aperture on our EMPAD data, we can get grain contrast, we can get magnetic contrast here and actually pull out these different regions. If we look at a grain orientation map, which comes from the center of the disk, we can now see grain orientation information. Now the EMPAD is not ideal because when you're, well, I shouldn't say it's not ideal. There are trade-offs and there are balances between using the quadrant detector versus the EMPAD. The EMPAD has a readout time that is finite. You notice it. And so it takes a second or so, it takes a few seconds to scan over this image. When using the 4-quadrant detector, the readout and the speed with which you can image is much quicker. And so while this provides more information, which may be useful for some experiments, there are other experiments, like looking at gallium nitride, where you need 63 picometers of resolution. You can't focus on that with a slow raster that you would get from the EMPAD. So imaging something like that on the EMPAD can be more difficult than it would on the 4-segment detector. But for things where the image is complicated and the signal that it has is convoluted, the EMPAD gives you all of the information. And now with our customizable virtual apertures, we can pull out the information we want. So in summary here, as I finish up, if we look at that image I showed initially is very pretty in HADF STEM, but showing some deficient regions and then some dislocation regions. The 4-quadrant detectors have shown that we're able to image the light elements, such as oxygen in this particular sample. And if we use the 4-quadrant summed, we can actually image this in an ABF condition, which will also show the oxygen positions. If there was magnetic or electrostatic forces we wanted to measure in this, we could also start to measure those using the 4-quadrant detector. And the readout time here permits the best live imaging. So for the best resolution, you would like to use the 4-quadrant detector if possible. With the EMPAD, we really opened up, you know, infinite's the wrong word, but just a number of possibilities that were more difficult or we were incapable of performing before. And so with one image, the number of processing possibilities that come to us are everything we've talked about and more. So we can process these images for DPC or iDPC. We can use it to pull out the light elements. Again, we can do orientation mapping and qualitative phase identification like I showed you. We can do strain mapping. We can start to do fluctuation electron microscopy. For all of these elements or all of these measurements and all these techniques, one of the most important things we need is to know our thickness. And PacBed is wonderful at giving us an accurate thickness measurement. And so, the EMPAD pixelated detector for collecting the full range of diffracted space is a game changer. It reduces many time-intensive experiments to just a few images, and now you can do it on a computer. So a couple takeaways that I would hope that you walk away from this is pixelated detectors are going to change the way we perform microscopy, you perform microscopy, and as technology improves, I really think you're going to see the growth of these EMPAD or pixelated detectors to the point that it might be one of the only detectors in the microscope because of how robust it is and what it provides you. Lastly, I'd say CEMAS is a one-of-a-kind facility. We really are unique. There is no other state-funded institution in the United States or abroad that I'm aware of that has what we have. There are some private institutions and endowments that have funded some nice facilities, but we are pushing hard. We have some of the best researchers in the world, and what we want is to work with you. We really want to find problems and things that we can help you solve, but then also helps us optimize and push the skill sets that we have at Ohio State and in CEMAS. So with that, I'll finish up. I think I've seen some questions come across, so I'll try to start answering the questions. I do, before people leave, I want to bring up, we have 2 talks coming up in the future. These dates are wrong. I apologize. It should be 1 week forward in time, so the 20th and the 27th. Next week, we have Below the Surface with Dan Huber coming up. Everything I've talked about requires a good sample and a thin sample. Knowing how to make that is often as challenging, if not more challenging, than the actual science you're trying to perform. So attending this talk will be really beneficial. And then the following week will be Hank talking on X-ray diffraction, an oldie but a goodie, something that is not exactly electron microscopy, but something that we use very much in our facility. So you can go to CEMAS for those events. And here are some things you can use to connect with us in different ways. So with that, I'll finish, and let me see if I can find some questions to answer.